Welcome to our class. Today we want to consider calculus of residue. In our last videos, we have considered how to calculate residue, and we have talked about residue theorem. The question now is that how can we apply this residue to solving some definite integral? So we'll consider the following definite integral where we can apply residue theorem. The first case is this. The first type of integral we can apply residue. When we are given a function, but this function f is rational, that is, it's in terms of a over b. So we can apply residue theorem when you are given an integral 0 to 2 pi only, and a function, a rational function that has sine and cos only. So we apply it. So how do we proceed if you want to solve this type of problem? We need to just recall that sine theta is same thing as z minus z this over 2i. Cos theta is equal to z plus z this over 2, where our z is equal to exponential ix. So that's our z, exponential is. From this place, if I differentiate it, because of this, okay, let's use theta. We are dealing with theta. So if I differentiate it, the z, if I differentiate this in, I will have exponential I theta d theta. You now observe that this I theta is still our z d theta. So therefore, our d theta is equal to the z over iz. So we need to take note. So that is what we are going to make use of. So at the end of the day, the integral will not be of this form. We will now write it in terms of f of z dz, which at the end of the day we can apply Cauchy integral theorem for Cauchy residue theorem, which is 2 pi I times sum of residue. But what is our c? We integrate c. C is a unit disk. What is unit disk? This is unit disk. So this is how we are going to proceed. So we integrate c in this unit disk. It will enable us to solve this type of integral. So let's take example. So we have our example 1 here. We want to evaluate this integral. So we are to use the residue for it. Now how do we start? Let me represent I by this integral. Then we'll put c here. C is a unit disk. This is 1 over 2 plus. So we use our formula that I gave for z. Our z is this over 2. Our d theta is the z over iz. So we now need to simplify it. And when we simplify, we should be able to get this. This is a quadratic formula. So in this place now, let's take our f of z to be 1 over z squared plus 4z plus 1. So since we cannot factorize it, it's better we make use of the quadratic formula. So from this place, we need to locate our singular point. And when we do so, use quadratic formula for this. So we see that z is equal to 2 plus this, and minus 2 minus this are the singular points or the singularities of this f of z. The question now is that which one will lie in this c? We have said that c is this disk. So which one? That is, which one will be less than or equal to 1 out of this? So root 3 minus 2 will be less than. But this one, minus root 3, although it's less than 1, but we need to take absolute value. We need to neglect the negative. So you see that when you take the absolute value, it will be greater than 1. So only this lies in the disk. So we write it as, but only this lies in the disk. So in this case, we make use of we find the residue. This is we should know that it's a simple pole. So the residue is limit of z tends to z naught. It's long. I don't want to write it out. Let me just write it as z naught. So this is z minus z naught from the formula. Z minus z naught. These are z naught. So if we put minus z, this will be this minus this. Times f of z. This is our f of z here. 1 over, let me put the over here, z squared plus 4z plus 1. Now we want to find the limit. These are z naught. We know that when we put z naught here, this will be 0. When we put this value here, it will be 0 too, because we got this value from this quadratic equation. So what we do is we quickly use quadratic L'Hospital rule, limit by L'Hospital rule. How do we do that? We differentiate z, that is 1. This one is 0 when we differentiate. We differentiate this. This is 2z plus 4. So I can now substitute the value. So this will be 2 into this our z naught minus 2 plus root 3 plus 4. And if when we simplify, we are going to get 1 over 2 root 3. So we have known our residue. So in that case, the answer will become, there is 2 over I here. This integral will become 2 over I times the formula residue theorem, 2 pi I times the residue. So this is 2 over I. We got this 2 over I from this place. Times 2 pi I times the residue is the residue. 1 over 2 root 3. So from this place, this cancels this. I cancel I. All we have left is 2 pi over root 3. In that case, we can now say that integral 0 to pi 1 over d theta over 2 plus cos theta is equal to 2 pi over root 3. So we have applied residue theorem to solve this real integral. Although we can still apply the normal elementary calculus, but we are looking at the application of residue theorem. Let's take another example. Example 2. Show that this is equal to this. So what we do is we'll follow the same format. We say that our I is equal to, let me take 1 over 1 plus a. You know our cos is z plus z this over 2 d theta. Our d theta is z over iz. And we now need to simplify this. When we simplify, we get this. When we simplify it, so we are going to get this. As usual, this is our f of z. We take our f of z to be this function here, and that will be f of z equal to this. Now we need to solve this function. We use quadratic formula to solve it, to find the root of this function. And when we do so, when we use the quadratic formula, we are going to get z equal to minus this plus this, and z equal to this. So these are the two singular points when we use the quadratic formula there. But only this, only you can write, but only z naught is equal to this lies in the disk, because our a is less than 1 and is greater than 0. That is a proper fraction. You substitute any proper fraction here, you see that, and you take absolute value, you see that it will be inside the unit disk. Now we find the residue. So the residue at this z naught will be limit of z tends to z naught. I will not write it because it's long. Z minus z naught times f of z. So this is our f of z, and f of z is over az squared plus 2z plus a. So as when we substitute z naught here, this will be 0. If you put it here too, it will be 0. That is indeterminate form. So we apply L'Hospital rule to it, and we differentiate this. That is 1. We differentiate this. This is 2az, then plus 2. So from this place, we can now substitute the value. The value of z is our z minus 1 plus 1 minus root a over a plus 2. Which, if we simplify, we are going to get 1 over 2 root this. When we simplify it, now our integration, I've used I to represent it. It will be equal to, there's 2 over I here. Let me write it. Then we can now write the residue theorem, which is 2 pi I times the residue. This is the residue that we got. 1 over 2 root this. This cancels this. This cancels this. All we have left is 2 pi over root of 1 minus a squared. And that is what we are asked to prove. So let's take example. Example 3, we want to evaluate this. Here, we are only giving for cos, ordinary cos, but this is cos 3 theta. For cos 3 theta, we can do it like this. You know, 3, there's 3 there. That will be z cubed plus z this over 2. But for easier one, we know that exponential I 3 theta is same thing as cos 3 theta plus I sin 3 theta. So that means the real part of this is cos 3 theta. So the best way to write it is this. This I can be written as the real part of exponential I 3 theta. That's the best way, so that it will be easier for us to tackle. Although we can apply this, but it will be cumbersome when we are calculating. 5 plus 4 cos theta will be z plus z this over 2. We're still using cos theta. We are still using cos theta. Now, we cannot turn it to complex function. So let me put the re outside. So this will be exponential I 3 theta here. We know that we have said that z is exponential I theta. Therefore, this thing will just be z raised to power 3. This one over 5 plus 4 into z plus this, that is for cos, over 2 times this z over high z. Then we now need to simplify this further. And when we simplify, we should have this. Don't forget there's I here. So let me put 1 over I there. So this is easy to factorize. This one is easy to factorize, unlike the ones we are getting before. So when we factorize this, we should be able to have this. So we should be able to have this. So in that case, from this way, you can easily determine our singular point. So we can now say that therefore z is equal to minus half, and this are the only singular points there. But only z is equal to minus half lies in that unit disk. So this is our f of z. Remember, our f of z is z cubed over 2z plus 1. Or simply, we can put this one there. Now, we can now go to our residue. Residue at that point, that is limit of z tends to minus half. Z minus z naught. These are z naught. Our z naught is minus half. It will make this place to be plus. Times f of z. This is our f of z. We write it. Now, we have written our f of z out. We can still simplify further. You can see they look alike, but we need to make them the same. So that is when we factorize this. So, and that will become this. As you can see, this is the half. So this one and this, they are just the same thing. So they now look alike. So I cannot put z to be half. Anywhere I see z, I will take the limit as z tends to minus half. And when I do that, we are going to have the following. This is half times this z cube here will be minus half cube over minus half plus 2. So we need to simplify this from our calculator. That will give me this. I've found minus 1 over 24 as the residue. Therefore, the given integral will become, there is where is it? You have 1 over y, the real part, that is mean of 1 over I, the formula is 2 pi I times the residue minus 1 over 24. So from this place, I cancel I, so this is useless because there's no real part and imaginary part again. 2 here 1, 2 here 12. So finally our answer is minus pi over 12. So that simply means that this integral, I've considered more examples on this, so you can practice the following questions. So we have the following. So this number 1, number 2, this number 3, the answer is given already. Number 4, number 5. So we have considered integral of this format. Let's consider another integral that we can apply Cauchy-Residue theorem for. So this is the type 2 integral of this format. This is improper integral of this f of s, where f of s is a rational function. So how do we integrate such using Cauchy-Residue theorem? So when we are given this type of integral and we want to use residue theorem, we integrate it in an upper half plane. So what do we mean by upper half plane? That is in a semicircle. So this is it, semicircle, in this semicircle here. So let's say this is the y-axis here. So and in this case, the real part, the singular point will be on this imaginary axis. So here we have minus r to r. Here we have this is an arc which we represent by CR. So we integrate in this upper half plane. Now, because of this arc here, so we need to consider the following theorem. We have the theorem here. Suppose f of z is a rational function, and we say that if CR, this CR is a semicircular contour, we let z is equal to this, where 0 is less than, theta is less than pi. Then this CR, the integration along that CR, this CR here, this curve here, will be 0 as we tend r to be infinity. So this theorem is very, very important. So it's a thing we can prove. So if we start from this place, f of z is z here. So when we take this will be 0 to pi here. F of our z is r exponential I theta, and our dz is that is, if you differentiate, this will be I r exponential I theta d theta. Now let's take absolute value of both sides. So by the law of integral there, when we take absolute value, this will be less than when we put the absolute value inside. This will be f of r exponential I theta. The absolute value of I is 1, and absolute value of exponential I theta is 1. So it remains r there and d theta. So let me bring my r here, and by Cauchy's inequality, we know that this is pi m over r raised to power n. That is if m is bounded. So that is f of z is bounded. Now what we have left is this. Okay, we don't need to bother ourselves. The pi will be there when we apply Cauchy's inequality. So we get this. Finally, there our answer is pi m over r raised to power m minus 1. So that is the integral. Now, as r tends to infinity, when we take the limit, so as r tends to infinity, pi m over this will tends to 0. Therefore, we can now say that c big R f of z dz will tends to 0 as r tends to infinity. I will take out, since it's under, so anything over infinity will give me 0. So this tends to 0 as r tends to infinity. So that completes the proof. Let's take example on this type of integral. We have example here. We want to evaluate this using Residue's theorem. So what we just do is, for this one, you only tend anywhere you see s to z. So this will be z square over 1 plus z square, then all square dz. And this one will now be this c here is this semicircle, so which I can quickly draw here, minus r to r, then c small r. So in this place now, it will be integrated along this minus r to r, our f of z, this is our f of z, dz, plus the whole of this curve here, the arc, c big R, f of z dz. By the theorem we just proved that this will be 0. So we are left with this. So we can now apply our Residue's theorem. So our f of z is z square over 1 plus z square this. Without stressing ourselves, we see that z is equal to plus or minus I is at the singular point, but only z is equal to I lies in the upper half plane, this place. So this one minus I is the lower half plane, so only z is equal to I lies there, and z is equal to I as double pole. So we need to recall our residue for double pole. That is 1 over, if I want to rewrite this thing very well, for clarification, before I do this, for clarification, this thing, since this is to be z plus I, z minus I, but there is square on it, everything squared. That is the expansion of this 1 plus z squared, which I can write as z minus I squared, z plus I squared. Now I can find my residue. So my n is 2, it's a double pole, so the formula is 1 over 2 minus 1 factorial. Limit of z tends to z naught, our z naught is I. So the next thing now is that we have z, since it's double pole, we differentiate. It's double pole, we differentiate once. I'm using capital letter D there. If it is twice, I'll put D square. Differentiate z minus z naught. These are z naught squared. If you remember, the formula is d dz raised to power n minus 1. But n is 2, so 2 minus 1 is 1. That is why I put capital letter D here to represent one derivative times this f of z. From this place, this one cancels this. So this is gone. It's 1. We don't need it. What we have left is z tends to 1. We want to differentiate. What we have left is this, that we differentiate. We want to differentiate this once. and that will give me, and that gives me this. Now I've differentiated it, it gives me this. I can now put z to be I. So this is I into I plus I cube, and this will give me minus 2 because I times I is I square, so this I is not there, minus 2. This one too will be 2I cube, so this will be minus 2 over I cube is minus I, 2 cube is 8. So finally there we have 1 over 4I. So therefore this integral z square over 1 plus z square all squared z will be equal to 2 pi I times the residue 1 over 4I. This cancels this over 2. So our answer is pi over 2 there. But remember, we have expressed this integral in terms of these two. But CR is 0. So that means this integral is same thing as this. So we can now say that this implies minus R to R z squared dz. In fact, it will turn to x now because of the real part. It will turn to x over 1 plus x squared all squared is equal to pi over 2. So if we take R to be infinity, in our theorem we took R to be infinity. So this will be minus infinity to infinity s squared ds over 1 plus s squared all squared is equal to pi over 2. Now this is the answer to this, but what we are looking for is 0 to pi. It's not minus pi to pi. Since this thing is an even function, so we recall that if a function is an even function, then minus a to a f of x ds is same thing as 0 to a f of x ds if that function is an even function. So in that case, this expression here will become 2 into 0 to infinity s squared over 1 plus s squared squared is equal to pi over 2. And if you make this formula, we divide both sides by 2. Finally, this integral will become pi over 4. So the required integral is equal to pi over 4. So that's our answer. So meet me in the next video for the continuation of the topic.